Now it's time for our final talk of the day. It's an invited talk from Pascal Paillier, and the title of the talk is Recent Advances in Homomorphic Compilation.
I hope you guys are not too tired. Long day, huh? Plus, I'm the only thing that stands between you and your cocktail. Sorry about that. Okay. Perfect. So for those who do not know me, my name is Pascal Paillier. I'm one of the two co-founders of Zama, also the CTO of that company. And I wanted to, so first of all, thank you very much for having me. It's very, every year, I mean, I say that this is the second edition, but it's always fun to connect with people who are so creative, who are passionate about fully morphic encryption, you know, with all these different aspects of the technology. It can be crypto, it can be hardware, it can be compilation, it can be optimization, it can be so many different things, use cases, you name it. And so it's always very humbling to meet with you guys and to see how creative and passionate you are. I wanted to take this opportunity of talking to you to submit you to a little exercise. And the subject I'd like to talk about today is homomorphic compilation. Because it seems to me that it's something that some people are working on. It's one of these new frontiers for FHE, like compiling automatically a kind of a naive program in the plaintext domain and converting that into a homomorphic equivalent, like automatically. And it's a little bit of a dream, and some people here are working on this, including ourselves at Zama, but it's not going at the pace that we would like. Like, we're not making as much progress as we should, because we're, of course, very, very skilled and talented people, all of us, but it's something that is abnormally hard, and I would like to open the discussion on this and to know why. And also to give you a little bit of an update about what we're building in terms of morphic compilation at Zama. So first of all, what is a morphic compilation? So the idea, and this is, by the way, the big dream, like the big vision, what ideally we would like to see, like on our laptops, like right now, it's you give as input some plaintext code, so a piece of code from Python, Rust, C++, whatever, doesn't matter. The one or the ones that have actually crafted this code are like general developers. They're not crypto savvy. They don't want to know anything about cryptography. They don't want to know anything about the compilation. They just, you know, the same way you're on the command line, you type GCC blah 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 .c minus o blah 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 .o. You want, and then it's done, and you don't have to care about the details. We want that for homomorphic encryption. We want a compiler that you just put that, it figures out everything, and then you can just deploy your homomorphic application, right? So the input, again, is a piece of code from somebody who doesn't know anything about cryptography and doesn't want to. Everything runs with this full-fledged compiler. Oops, sorry. So the compiler would do all the work here. Like, it would convert the input code into some kind of an FHE circuit. So it's always about, we're always discussing about circuits because there is this data independence problem. You know, how do you compile the factorial function? As soon as you need to branch depending on a condition that depends on an encrypted input, you cannot branch at runtime, right? So you need to kind of regularize the algorithm first to make it agnostic to, so that the control flow does not depend on the data anymore, at least not the part of the input that is being encrypted. So there's this kind of consideration that do not exist actually in actual compilers, like in classical compilers, but we have to face these kind of issues with homomorphic compilation. There is a phase by which we need to regularize and get rid or address any conditional branching, and so all the ifs and the like. So that's why every time we think of an homomorphic like runtime representation of what is of the processing that is being done, we always refer to a circuit because the circuit is always like data independent. The structure, the topology, the entire data flow does not depend on the value of the input. And so it's always the circuit that is like the support in our minds for what is a homomorphic execution, what is homomorphic processing. Is it really, or is it just a part of it? And can we actually have homomorphic programs? It's that kind of stuff we have to think about when we try to define what exactly we mean by homomorphic compilation, because it's not a clearly defined notion. It's something that's in the air. We talk about it, we try to build it, but what is it exactly? What is the perimeter of what it does? You know, I'm not sure it's actually very systematically understood from a scientific perspective. I don't think it is. But so if we simplify this kind of a debate, the full-fledged compiler would take this input code, convert that into an FHE circuit. That's the way we look at it right now. And then it would optimize automatically. Again, this is like the big dream, the dream compiler. It would optimize that circuit completely at the topological level, and also the crypto parameters would be found like automatically, and the best set of parameters would be selected for that circuit. Okay. And finally, we have a phase where the compiler actually generates an executable directly from this parameterized, topologically optimized circuit into an executable for a given target architecture, which, by the way, because this is again a dream compiler, could support like any kind of target architecture we may want, from x86 all the way to any kind of ASIC, and should be able to support like any kind of interface with a specific hardware architecture. So this is what we want to build. And actually, if we don't at some point have some kind of tooling like that, FHE will never be adopted. Because in this room, I mean, we're very talented people. No worries about that. The thing is, if we want to see FHE being globally, I mean, adopted at a global scale, FHE needs to be, we need to empower all the developers out there with the ability to develop homomorphic applications. And that should be painless, and that should be fun for them, and so that they could express their natural creativity and focus on their code, like the input to the compiler. And it's kind of our job to support what's going beneath, you know, behind the hood. And behind the curtains, everything that I'm talking about here should happen automatically. And okay, maybe what we can allow ourselves to say is, instead of having something that compiles in half a second, maybe we can take 10 minutes. Okay. The developer will allow us that, like 10 minutes is okay. You know? But I mean, apart from that, it shouldn't be very hard to operate. And now the harsh reality, what's actually happening for real. So the story here is completely different, right? Because first of all, the developer is not using a compiler. There is not yet a full-fledged compiler, the one that I was talking about. We're getting closer to that vision, but for now, it's not like fully operational, not in the way we would like to see it. So right now, what's happening is that, and this is like the majority, the vast majority of the cases, instead of a compiler, what's happening is that there is some kind of FHE library. So there are plenty of FHE libraries out there. The developer is actually a cryptographer or somebody who is crypto savvy and who tries to do their best, like implementing something. And and what's happening is that there's directly some code that is targeting the library, and then with a general compiler, this generates an executable that you can deploy and try to benchmark and everything. Okay, So this is mainly what people are doing, right? Right now, this is happening, not the previous slide. This is happening. And so when you look at what's happening exactly, the input code is actually already a circuit. It's just a formulation of a circuit. Maybe it's a little bit more verbose and everything, but the developer has to know in order which operation supported by the library is needed at which point in the circuit. So it's just it's not fair. It's like we're asking the developer to do all the job of the compiler because we don't know how to do that automatically. So the developer has no choice but to be crypto savvy, to have a notion of what an FHE circuit is, because basically the input code is just an FHE circuit calling these basic functions supported by the library, and that's it. So it's a complete. So it's normal. We have to start somewhere, right? And in the end, we have what we want because it's an homomorphic app, so it's perfect. But but it's excruciatingly difficult. It's super hard, even for us. It's very hard to do. And very often we don't even have a clue about what we're doing because we're just looking at what's going to what's going to happen in the end. We're going to extract performances, and maybe we'll say, maybe I should change this here in the input and see what happens. How can we help the world to adopt FHE in this condition? It's too hard. So the input code must be a circuit. So it means the developer knows exactly how to craft the circuit. The crypto parameters are to be given by hand because they're going to be hard-coded or maybe given in a header file or something together with the input, right? Because the library doesn't know how to automatically generate the parameters. There is hardly even a notion of what a circuit is in the library. The library supports the basic blocks, like the basic operations, and that's the job we see in the library. So actually, I'm a little bit harsh here because people are trying different approaches. They're also trying to work on synthesizing a circuit or, given a circuit, automating the generation of the optimal parameters. So there are pieces here and there, but we're still not at the position of the slide before where we had like this Dream compiler just going all the way through. So this is the reality of what's happening today. And we can ask ourselves as a community, what is exactly blocking this transition? Oops. Is that me or? Is it? Okay, sorry. Okay, so what exactly is blocking this transition? Currently we're more or less here. There are initiatives for compilers, or I would say ingredients for compilation, or semi-assisted, semi-automated pieces that actually help the developer, the one here on the left, to actually address some of the points I was talking about, generation of parameters, or the topological optimization of some circuits. So the developer would start with a basic circuit that actually implements the function, but that would give that to some kind of an optimizer that would optimize the circuit given a certain cost model. But on the other hand here, what we want is the dream with the compiler that does everything. And we need to go from here to there. And that's actually a long path, because if we see what has been happening in computer science, compilers arrived, people were starting to develop in assembly code on punched card before compilers were invented. So everything was written by hand, so they were there. But in a few years, they got there, right? Compilers suddenly appeared, and with them, high-level languages and ease of programming and deployment and reusability and so on. And so I would like just to discuss with you, what do you think in this room, for the people who are actually involved in this kind of thinking and kind of activity, what do you think is right now blocking this transition towards the Dream compiler? What is it that you think is preventing us from succeeding in building this? You see what I mean? Or does somebody have an opinion? Okay, plenty of people over there, I guess. Okay, hands are rising. Maybe I could use this.
Optimizing circuits is an extremely hard problem with like even more or less impossibility results.
When you say optimization, it's a topological, like the number of gates in a Boolean circuit?
The number
or
of
the
gates,
depth,
or even like the depth, everything to get like a practical computation, we need like optimization.
But in practice, we do that. Like you can ask, you know, you have tools for hardware synthesis and for circuit synthesis, tools that are pretty efficient, right? Why not using them?
Okay, maybe I assume at the moment that with the current performance of FHE, we wouldn't have to do better than current optimization tools to get something practical out of it.
But if you look at it, it has nothing to do with FHE. It's like how, if you want to look at the Boolean side of things, it's just about generating an optimal Boolean circuit that represents your function. And this is what the people in the hardware industry have been doing for decades. They have tools. There's an open source tool which is called ABC. You can download from GitHub. You can use it and you can actually generate circuits.
Okay,
so
yeah.
You see?
I see.
But
yeah.
Sure, that's what comes to mind like immediately, which is basically why. Sorry, to fix that. Which is a very good point. I mean, we need optimized circuits, and so. Yeah, it seems that this is something that we're not very good at right now. Like there is a piece that is missing. It's normal because many care about crypto and security, and so we're not like necessarily experts in Boolean circuits and hardware synthesis. But there is a whole lot of results and tools to be, you know, imported into our field and used. Yes.
Yeah, I think one of the difficulties is that it's apparently impossible to decouple circuit synthesis and parameter selection. I don't think you can attack these two problems separately.
Yeah.
You're welcome.
So that was the next slide, actually. But yes, exactly. So if we look at what we mean exactly by this full-fledged compiler, if you zoom in that box, you necessarily have to find these kind of ingredients in a way or another. Maybe they're not sequential. Maybe there is some, I don't know, some things that are being done in parallel or cyclically, or we don't know exactly, but it should look like that. There should be at some point a generation of an FHE circuit, basically, so this is the question that arises: how to synthesize a circuit given a plain text code. And then we see mentally that there is a disconnect, because in terms of what it means, in terms of technical achievement, we see that as two separate things. But actually, yeah, it may be not as separate as we think, which is the point where you need to optimize the crypto parameters. Given a certain circuit, you want to optimize the crypto parameters. But the fact of seeing them one after the other seems very, very naive indeed. And it is highly possible that actually you need to do both optimizations at the same time. Like you want to probably, guided by the optimization of parameters, influence the optimization of the circuit, and vice versa, like the other way around. Yeah, but we have no clue right now what this means. I mean, we don't have a clear definition of what a circuit is. It depends on the scheme, it depends on the library, it depends on the vision. Are you allowing the circuit, for instance, are you forcing the circuit to be completely defined statically? Or do you allow, for instance, a certain sub-circuit to be repeated a variable number of times, knowing that that variable is in the clear and given as an input to the circuit? See what I mean? Are you augmenting the notion of circuit with an if? Or are you like, okay, so there is like I wouldn't say a spectrum, but there is little bit of a distinction between a circuit and a program, right? And you have all these like execution models and equivalences between these, and so we know so little about all this that probably this is what's blocking the way to actually succeeding. But it's yeah, I mean these two questions are actually very valid. Would you see something else like that needs to be like improved before we can actually do all these things? Well, code generation, we already know how to do that, right? Once we have some kind of an intermediate presentation, we can use the back end of like LLVM or something to actually generate some code for a given target architecture. But yes?
I think you need more applications, because more applications mean more money. More money. Because, okay, so how does this work in the real world? Not in the real world. For the rest of computer science, right? We are in the real world, right?
I think it's meant to be, in the real world, there's a guy over there who is doing research, or, I mean, for a company or in academia, who's trying to demonstrate the feasibility of a certain application, right?
If you go to at the back end, if you have the circuit guys, right? These people can produce, you know, if you talk to Synopsys, these guys, they spend billions on their compilers.
Right.
Why do they spend billions on their compilers? Because they've got a market worth many billions. So they spend billions on the compiler. And that's the kind of expertise we need in this room. If you look at the back end, not the people playing around with stupid new languages, the front end of compilers, the people doing the back end of compilers from LLVM downwards, there's lots of people working on that. They spent billions on that. Why have they spent billions on that? Because there's more billions of money to be made. We haven't got the people in the room now who can do that little, the bits, the missing piece of the jigsaw puzzle.
So who do you think we should import or invite in our community to help us?
I think we need people from expertise, from Synopsys, from the people who do the FPGA compilers, because Synopsys is doing circuits, FPGA compilers are doing LUTs.
Yeah.
You know, we can have people who are doing the back end of, you know, like the back end of GCC. You know, so these are the people we need, because they are compiler experts, and they've spent, and we want to reuse their work. We don't want to borrow their work, because we're not experts, we're idiots, right? So we want to actually use their expertise, and all of that billions of dollars worth of research and development they've done on 30 or 40 years.
Yeah, I see the point. But can we, though? Because, for instance, if we think about circuit synthesis, in the hardware industry, they focus on Boolean circuits, right? Because it goes to, it's mapped to a technology afterwards. It's, you know, it goes to fab and everything. There's a process. But actually, when you look at the FHE scheme, they can support like wider message spaces, you know, plain text spaces outside of just F2. So you can play around with like small integers with the case with TFHE, or larger integers. You can play around. You can also encode them in a certain way. So is it known that can we actually extend Boolean circuits to arithmetic circuits where you represent like small integers, but maybe small modular integers with modulus, a moduli that could change across the circuit, for instance? This is the kind of theory that we need. Understand what these circuits are, how to generate them, how to optimize them. Is it something that we can get immediately from people from Synopsys?
There might be stuff in the past, because if you go back to the early 70s, computers were created with RNS arithmetic in hardware. Okay, and then they would compile down to RNS arithmetic, because, you know, before you had the Intel 4040 or whatever it was. Yeah, so 4004, sorry. Yeah, so there are, in the history books, there might be some very old engineers, but there is going to be a history there that we should leverage rather than try and reinvent the wheel.
Yeah, but we're aware of RNS and the like, right? So we should be able to tackle that problem on our own. If it's just about RNS, I don't know. I know. I'm trying to dissect together with you why it's so hard for us as a community to move forward to the point where we have this dream compiler that everybody wants.
Yeah.
Yes.
I think there is also a problem of scale.
Okay.
So in the sense that, so for example, if we take a CPU program, so between some C code and a CPU, a compiler that does a naive job will already have something that is, I'd say, reasonable. And of course, if you go from 0 to 09, maybe you will gain a factor of 100. But even the non-optimized code in plain text is already reasonable. Whereas in MPC, it's not the case. We have this gap of 1 million. So we in some sense, the gap is much harder. We expect the compiler not to have a factor 100 compared to the non-optimized, but more 1 million. And that, in my sense, is very hard.
Valid. Absolutely. Sorry, you wanted to say something?
Because I don't fully understand the question, to be honest. Yeah.
Okay.
Yeah, because so we have the Google transpiler.
Yes.
So we are already there. Yeah. So we have like a compiler, yes, that compiles from C code or C++, well, C, to a circuit, yeah, that is then executed, yeah, by a FHE. Yeah. So
yeah.
So what is the question actually? So I mean, so why we are not there? Yeah.
So you think we're actually already there?
I mean, you know, so maybe it's not the most efficient for now and so on, yes, but when you want to make a check mark, yeah, whether we have some compilers, yeah, then we have.
Yeah.
I think there are also some compilers that compile code from Python to, well, some now I don't remember the name, yeah, so that compile, yeah, some Python, like a subset of Python code and so on, yeah, to a certificate, yeah.
Yeah, sure. Concrete NumPy does that, but
oh, yeah,
I'll talk about it later.
Okay,
typically. But do you know how parameter optimization happens in Google's transpiler?
So in the transpiler, yeah, they don't really need to optimize anything, yes, because so they have a Boolean circuit, yeah, so they just use the Boolean FHE that has bootstrapping, yeah.
Absolutely. So the parameters are actually fixed.
Yeah, exactly.
Do you know that it's not optimal?
How? Wait a moment. Whether the parameters are optimal?
No, I mean that this might. I mean, having just a couple of gates that are used with fixed parameters to realize with a Boolean circuit a given function, like a big multivariate function, to decompose that into a base of parameterized gates may not be optimal at all. We have no clue.
I don't think I understand still.
Okay.
We can maybe talk offline.
So maybe you can take like a Boolean circuit. You can take some of the gates together, form LUTs, like from 4 to 3, implement the LUT as a single gate with its own parameters. But overall, you would gain because the number of LUTs now is much smaller, or the depth maybe is better, or the critical path is better, or there is some form of optimization. You see what I mean? And for some functions, you can do that efficiently. For others, maybe not, or maybe not with the same base of LUTs in the first place.
I see.
So I got your point. Yes, it already does something like that. Is it the solution then? Are we done then?
I mean, you mean like the ultimate solution?
Yeah. So are we ready to tell the world, like, you can embrace FHE, just download the tool and play with it?
No. So to embrace FHE, then it has to be faster and so on. Yeah.
Okay. Right.
But no. Okay. Yeah.
So we can say that
I see what you mean.
Well, I'm very ambitious. I'm talking about the dream compiler. So of course, if it's a dream, but at some point we have to wake up and catch up with reality. But yeah, somehow we're getting there in a way. I totally acknowledge that. The important thing here was the cost model. Actually, the parameter optimization, to optimize the parameters for a circuit, if the parameters that you're using are not like completely fixed, but they depend on the circuit that you're synthesizing, you actually need to select these parameters the way Damien and Sam presented earlier today. You need some form of a cost model. You need to know what the operations cost, how they're like the ratios between doing an FFT and doing an NTT, so that you can select the best option in the final executable. Like you need to have all that. Sorry, there's somebody also who wanted to react.
Yeah, so
Yeah.
this is just a thought. I'm not sure if it makes sense, but in the CK world, like zero knowledge proving, it seems that similar things are happening at the moment. They are also building compilers and so on. So is there some relation? Can this community here learn from the CK community, or? That's
a super good question. And very often when you start discussing circuits, people say, oh, but even compilers, people say, oh, but in ZKP, we're doing the same thing. In MPC, we need the same tools. So there must be some kind of a common, like, you know, we should have some common foundations between FHE and MPC. But I don't know. I don't know all the state of the art there is to know about how circuits are generated and work in these other settings. In our case, it's probably, yeah, the constraints must be a little bit different when we talk about circuits for FHE, optimal for FHE, rather than for other, like for MPC. There must be like different constraints, but.
I just want to point out, there's been sort of recent work done for like joint compilation for like FHE, ZKP, and MPC. It's called Cersei out of Stanford. And the folks who worked on that paper, like Fraser, Riyad, Alex Asdamir, will actually be at Real World Crypto if you want to talk to them about it. Okay, so cool. There is, yeah, pretty recent good work there. Cool.
Okay. Interesting. All right, there's somebody up there. Yeah.
So as was mentioned before, part of the problem with the parameter optimization is that it's highly dependent on the backend, on how you actually implement.
Yes.
So that's part of the problem. Why I think, as a general comment, one thing that we could definitely do better is communicate better how we implement our backend to experts who have done this before in other contexts. So even people working in programming languages and compilers, if you look at these conferences, PLDI, POPL, they somehow try, the specific groups who are trying to build compilers, they're coming from compiler expertise. They do all the stuff that we also do, analysis of intervals, etc. And that experience that they have can be useful because they have also their big bag of tools that we don't know about. For example, recently we spoke with some people doing compilation, so that the Scala community, and they were talking about this compilation in stages, which is a very powerful technique that apparently applies to our settings as well. So I think what we just need to do, and that has to be a targeted effort, we need to more clearly communicate our backend technology. And that's difficult for these people from compilers because this includes obviously a lot of number theory. You need to explain a lot of concepts that they probably don't feel very comfortable with. So maybe we need to bridge this like scientific communication.
Yeah, fair point.
Yeah.
Touching on the MPC and FHE thing, for 10 years, despite the theoreticians keep talking about circuits in MPC, in practical MPC, no one's used circuits. So circuits are not used in MPC anymore. They haven't been for about 10 years because there's a completely different underlying model of computation underneath. So, yeah, so there is very little similarity between the two.
I was waiting for you.
It's going to sound like a broken record there. No, to answer a very specific question about like the ZKP and the FHE world, as somebody who's written an FHE compiler and is currently writing a ZKP one, they don't really share any optimizations beyond trivial ones, right? Yeah, getting rid by ×1 is a good idea in both, but in general, they're just so completely different cost models. And most of the ZKP world works in constraint systems, right? R1CS, etc. And that's kind of the de facto intermediate representation. just like circuits probably aren't the right one for FHE, R1CS is probably not going to be the future of ZKP, but it just means that most of the work just isn't directly applicable. And actually, with the work from Stanford, they sort of saw that when they started looking at FHE, they ended up getting performance benefits from completely different parts of the stack than they were getting in the ZKP world.
Thanks for that. I see that time flies. So what I'm going to do is that I'm going to, okay, so you can see the conclusion is, okay, this is a debate. It's going to, probably the discussion will go on for years before we actually can make sense of all this and know exactly how to specify or build compilers. But in the meantime, we have to create biodiversity, you know. We need to try, you know, experiment and see what happens. Yeah, what I was going to say with the cost model is that at some point to optimize parameters, you do need a cost model. And the cost model is coming from the execution model, the way things are going to be run at the end. And so this necessarily comes from very low down the line, like how the executable will be actually executed on the target architecture. So it's the architecture that actually defines the cost model that is being used by the optimization of parameter. And that's just assuming that we're given one FHE circuit. But in reality, it could even happen before, because you could like generate plenty of good candidates for the circuits, parameterize them all, and select the one or the ones on that are the best on the Pareto front, like that are the best simultaneously for time of execution, size of keys, and ciphertext size, and blah, blah, blah. So even just having that as a question mark means there is no clear separation between the circuit synthesis and parameter optimization. I think it was you who raised the point at some point. So this is true, but at some point, in order to make progress, we need to decide. And it's easier when you build a compiler to make it modular, right? So even if you're going to just generate one circuit, hoping that it's probably the best, it's already some progress, right? But this is the kind of question that I currently have no answer, like no definite answer. But what I can show you is what we have decided to build very quickly. Also, well, okay. The same story, you know all this, right? So blah, 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 noise, blah, 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 increases, blah, 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 bootstrapping, blah, 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 programmable bootstrapping. Neural networks, activation functions, but programmable bootstrapping. So easy with bootstrapping, blah, blah, blah. Kolmogorov superposition theorem, the fact that you can decompose any multivariate function into a network of univariate functions, or have an approximation using, for instance, rich decomposition, so that there's a whole theory that tells us that any multivariate function, we know that for neural networks, but it goes beyond neural networks. For networks of lookup tables, and the linear part in the network being either just addition or multisums, meaning linear combinations with integer coefficients, we can replicate any function. So what the Kolmogorov theorem says works actually over the rails. When you do things in the encrypted domain, well, everything is going to be discretized anyways. So there is still missing like a theory that will be adapted to the discretized version of the Kolmogorov superposition theorem. We're still looking after that. But the dream compiler, I mean, for us, is you give a functional description of the function, the big multivariate function that takes the xi's and returns the yj's, and it figures out a circuit like this, a circuit of univariate functions. And every function is actually a homomorphic lookup table. The linear parts are easy. And so, of course, the minimal depth for us is optimal because we're in a context where we can parallelize on the same layer. But if you look at the throughput, what matters is actually the total workload. So you want to generate a circuit with minimal size, not minimal depth. So there are already like these different notions, but this is for us, like this is for TFHE, our dream compiler. It should be doing something like that. So what we're building, the concrete compiler is actually, so I'm going to skip that. So with TFHE, what you can do is basically alternate between multi-sums, linear operations with integer coefficients, and not even like ciphertext multiplications, although we do have this functionality, but it's not like natural for TFHE. TFHE is very good at supporting like linear operations and homomorphic table lookups. And so supposedly, I mean, this is what we feel. Normally with homomorphic lookup tables, you can simulate a lot of things. Suddenly you have everything that is nonlinear. So you should be able like to, you know, create a network that actually mimics the function that you need. And the typical example, when you want to multiply A and B, you can see the product A times B as a difference between two squares, like A plus B square over 4 minus A minus B square over 4. That gives you A times B. So there's a way to reduce the multiplication, the bivariate function of multiplication, into just linear operations involving univariate functions. So this is like a trivial decomposition of the product as a network on the previous slide. So in the end, what you end up with TFHE circuits is basically graphs, DAGs, of multi-sums interleaved together with lookup tables. But you can program all the lookup tables, and you can actually have not only bits in there, but also like small modular integers, small meaning up to something like 8 bits natively, and then we have like mathematical emulations to extend this precision, as was told earlier this day. But so basically a TFHE circuit is something that looks like that. Okay, we can switch the moduli when inside the same circuit, but I think I'm going to way too many details there. So in a nutshell, what the concrete compiler is doing is that it takes as input basically the plain text code I was talking about earlier, but under the form of a DAG. This is the plain text DAG, so with the natural naive plain text world oriented operations, the natural ones that the developer are actually using. And this is provided as a representation in MLIR, which is, I think, really the best framework for homomorphic compilation. I don't know if you guys are familiar with MLIR. Are there people not familiar with MLIR? Nobody's raising, okay. I see a couple of hands. I see a few hands. MLIR is actually a framework to express, so in compilers you have, usually like in an LVM, you have one single language called the intermediate representation to represent every data structure that the compiler is going to transform up until the end. So the first thing it does is the front end is actually taking the input, lifting that into some object that represent the initial code in this intermediate representation. And so it's a form of a data structure. And then this is going to be transformed, iteratively optimized, and then it goes to the backend where it's transformed into machine code. And so in the middle hand is working on this intermediate representation. MLIR is generalizing this by saying, why having one when you can have as many as you want? And so what it does, it allows you to create intermediate representations of your choice. And so you can start with, so they call that dialects. So MLIR is some of a meta tool to define intermediate representations as dialects. So what you do is, depending on the different operation, if you want to decompose what the middle end was doing like very monolithically, you can actually do that in a modular fashion by just splitting that into phases and using different intermediate representation, different dialects. So you start by uploading, lifting into some dialect, and then maybe you can lower, they call that lowering, into another dialect, although you may not lose anything if the lowering is like 1-to-1. You can come back if you want, and you have like this graph of operations that are supposed to do the compilation, whatever this means. And at the end, it's going to end up with a backend. But you can invent dialects that are the most optimal for the type of operation that you want to do at a certain point during the compilation. So this is really something that allows us to represent what a plaintext DAG is, what an FHE DAG is, what the TFHE circuit is, and specify that very formally. And so right now, this is what the concrete compiler is taking. It does topological transformations, but as I was saying earlier, it's essentially generating like one circuit. Although there are options and there are things that can be improved in there, we end up with this circuit that I was telling about just before. And then this is exactly the same thing. It's now a TFHG DAG, so we're now in the world of homomorphic programs or homomorphic circuits. It's also an MLIR dialect. It's just a different dialect. And as input, it comes with no parameters, no crypto parameters, like they're empty, they're just placeholders everywhere for the crypto parameters. And then the optimizer that Sam and Damien were presenting earlier is actually going to optimize this and to fill in all the blanks and to put all the best crypto parameters we can find for this circuit. Once this is done, it's actually very naive. It's actually much more complex, but just to give you like a sense of what we're trying to do. And after that, we go into the memory and parallelism and orchestration layer, which is basically the moment where you decide how the runtime of this DAG, you have to transform the DAG into an executable. So you see exactly how to allocate the resources at the right time, scheduling of operations. If you're running on a homogeneous or heterogeneous execution environment with 3 GPUs there, 96 CPUs there, maybe an FPGA, whatever. So this is the moment where you basically figure out how the execution will happen and under which conditions. The target we had initially was concrete core. So meaning that here we had our TFHE low-level library that was optimized in Rust with the crypto-native homomorphic operations. We decided to change a little bit that path. And concrete core also had like concrete lib, which is outside of native crypto operations, like a layer of higher level constructs and data types that you can create based on the native operations, like larger integers, for instance, the one that exceed the native precision offered by TFHE. But we decided to do something else than that. We decided not to go with the dependency with concrete core here, but to separate somehow and actually to generate code right away. Not targeting a library, just generating machine code, the final code, which kind of resonates if you think of in terms of virtual machines. When you compile something, you can generate bytecode that is going to run on some virtual machine. That's a way to separate, put a line in the sand between the compiler that's going to generate the bytecode that will be universally executable on any virtual machine of that type, and the hardware and everything that's happening in runtime. Both are separated. Actually, going to a VM approach can be interesting. There are pros and cons. There are pros because the mental model for developers is simple. It is portable. It's universal. So it can ease, the emergence of a community of interest in the compilation part. The problem is we know that it's not optimal. We know that it will, if we can generate the code on the fly, it will always be best in the end. And this is a lesson that we've learned after like plenty of experimentations, like the Java virtual machine and the like. It's always best in the end to generate the code with a good compiler. And the compiler knows exactly what their hardware is doing, the low-level instructions and stuff. So it's not abstracted away beautifully, but not efficiently by a virtual machine. But so we've decided directly to generate the code because I mean targeting a library or generating bytecode for a virtual machine is basically the same thing, right? You're just accessing an API of functions. And the thing is, we can also like integrate like specific hardware in the toolchain because we're just using LLVM as a backend. So LLVM is this rich ecosystem of instruments to actually generate code on a number of target architectures, and we can also add other architectures like specifically designed to accelerate some operations. But the important thing is the cost model again. We need the hardware or the execution model to give us a cost model to run the optimizer. And Damien and Sam talked about that. Like we need a cost model to actually find the optimal parameters. There's also something else, which is we need to generate parameters for what's going to happen in the front end, like the client front end, not the cloud part. What's happening in the client who will be generating keys and encrypting and decrypting on the fly. We need to also to provide some kind of executable, some kind of crypto front end for that client. So everything can be actually generated directly by the compiler. But we also decided to keep like the internals of Concrete Core and Concrete Lib and actually give it a new name, which is TFHE.rs, because everything is written in Rust and specialized for TFHE. And this is still something that we're maintaining and investing a lot of time in because it's made for you. It's made for the poor guy I was showing before, the poor cryptographer, you know, on their own that are trying to handcraft their own circuit and make it work with a certain use case in mind. And yeah, you need that because you still need that at this stage because we're very creative people. We need to test our ideas. We need to compare them to each other to see how they compare. Also, it's very inspirational to see how people, by doing things by hand, how to replicate that knowledge and expertise into automated tools. So it's always something that we may want to work with. And of course, the best performances right now are obtained not with any compiler, but are obtained with handcrafted circuits made by cryptographers. It's just that it's not scalable. And if we want FHE to be adopted, it has to be scalable. It has to be easy. Okay, on top of, I'm going to finish with this, I'm sorry. I said that I was standing before you and your cocktail, so you're going to deserve your cocktail, definitely. So on top of the compiler, because you have to provide a DAG in MLIR dialect, I don't know, I have no clue how to generate that by hand. And I don't want to know how to do that by hand. So we need some kind of a front end, and this is what's happening. We have, we have something called Concrete NumPy, where basically you give like some Python code, right? Some naive Python code. It just relies on NumPy. And it's going directly to generate an input for the compiler. So it's actually, now it's Python code, like any data scientist is working with a Jupyter notebook, or Google Colab or whatever. So you can address not only machine learning and the like, but actually any kind of data processing. It's really meant for data scientists. But then on top of this, you also have like Concrete ML, which is meant for machine learning experts to actually generate Python code for models and for homomorphic inference. You can use Concrete ML, so you can, there's Benoit somewhere. I don't actually see him, but oh, he's over there. Who is heading the team, who's building these fantastic tools. So you can actually use Concrete ML on top of Concrete NumPy to actually perform homomorphic inference for like linear models and generalized decision trees, and also like any model, it just has to be exported in the ONX format. And so you can use your own torch model. There is like tutorials that Benoit and Benoit's team have put together that show you how to do that. The thing is, to be compatible with, to be FHE friendly, everything has to be quantized. meaning the weights have to be quantized and to be optimal, and basically the activation signals have to be quantized. But fortunately enough, in machine learning, quantization is something very, very trendy because they want to put everything on edge. So it has to be as lightweight as possible. You have TPUs where you use 8-bit quantization. So actually our quantization is a little bit different than this one, but you catch my drift. Like this is something that is very, very trendy in the ML community. So you can basically do a post-training quantization, take a model with full precision using F16, F32, F64 for that matter, even if it's an overkill. You can take a model like this and do a quantization post-training, but it's never as good as when you do it on your own. You do the training in a way that is quantization aware. And you can do that with packages like Brevitas, which is why Concrete ML relies on Brevitas. So basically you have your data set, you have your network topology, you're going to do the training on your own in a way that is quantization aware. So it's QAT, quantization aware training. And then you get much better accuracies. And then just going through the entire stack, you'll end up with a homomorphic equivalent of your model that is ready to be deployed for your target architecture. So this is something we think is going to be appreciated by developers. Of course, we're on our way to this Dream compiler. This is not, again, this is not the Dream compiler. There are features or ingredients common with the Dream compiler, but I think it's kind of a common dream, and we're trying to get there. So this is currently the solution that we're building. And with that, if you want to give it a try and go there, you can download everything on GitHub. Somebody told me that the Concrete compiler was actually not open source, but the executable was downloadable. But it's going to be open source like by the end of this month. It's because we had like internal private releases, if you will. But now things are going to be really fully open source. So you guys can take a look at at how we do the optimization, how we do the transformation, the MLER passes. There's a whole like tool chain and pipeline of operations being done. And of course, if you want to discuss that some more, you can always go to the Discord of FHE.org and discuss with us. We're always open for discussion on this. And the more we can do, to advance FHE, not only in terms of science, but also in terms of engineering, in terms of sharing experiences for developers. It's the beginning of a new era. I mean, I'm very passionate about it. I've been working pretty much all my professional life on homomorphic encryption. I did my PhD on homomorphic encryption. It wasn't fully homomorphic encryption at the time. Nobody was thinking it was actually possible, but it was already homomorphic encryption. So this is kind of a passion for me. Sorry, I'm very talkative. You'll have to stop me. But if you want to go on with the discussion, you can always go to the Discord server of FHE.org. And with this, I think we all deserve a cocktail, me included. Thanks.